To avoid the effects of ISI, three solutions were proposed by Nyquist. The first one is to use a line coding that is absolutely band limited. That means we already saw that such a rectangular pulse will produce a sinc function in the frequency domain. That is, it will produce an infinite bandwidth frequency in the frequency domain. So he brilliantly thought that if this rectangular or square pulse is producing a sinc function in the frequency domain, and when we are cutting the additional frequency components, this pulse shape is changing. So there must be some pulse shape that produces a square or a band limited or a sharp cutting frequency band in the frequency domain. So he suggested that we shall use such a sinc function in the time domain to produce a band limited frequency signal. So actually this effect is complementary. When the signal was time limited, it was not band limited. Now when the signal is band limited, the problem is it is not time limited. As we already discussed, this sinc function extends to infinity in both directions. So now this is in a time domain. That means this sinc function signal should start from an infinite time and it should end at an infinite time only. So in practical, it is not possible to implement a sinc function in practical. So the next solution was to use some other pulse shape which is similar to this one, because our theory was it is okay for the pulses to overlap somewhat, but there should not be any overlap at the sampling instance. That is the only criterion that should be met. So we can choose any signal shape that resembles to this one, but also is possessing the quality of no overlap at the sample instance. So Nyquist himself suggested another waveform which looks like this and possesses most of the qualities of the sinc function. Such a signal is called a raised cosine signal. So it will look like this. It almost looks like the sinc function, but it is not extending up to minus infinity or plus infinity or any infinite time periods. So it is a time limited signal. So it will not be band limited as much as the sinc function's frequency spectrum, but there is a trade-off. That means there will be a roll-off factor that affects the sharp frequency band of the raised cosine signal. So this raised cosine signal also will have the properties of this sinc function, but it is not extending up to infinity, and this decay is fast, so it will be ending soon. So the suggestion was to use a raised cosine pulse instead of the sinc pulse, and the third solution was to use a equalizer at the receiver end. We are not discussing about that. These first two we will see in detail. So the first Nyquist criterion for zero ISI, as we discussed, it was to use a sinc pulse. So what he did is he found out the condition for intersymbol interference, that is at the sampling instant time t equal to 0, the pulse amplitude should be maximum. and at all other sampling instance the ISI value should be 0. ISI value can be present, but at the sampling instant, here you can see that this is the sampling instant. At all sampling instance other than t is equal to 0, the amplitude should be 0. Only that pulse should have an amplitude of 1 or the threshold or maximum amplitude. At all other sampling instance, the ISI value will be 0. That is the theory behind this. So the only function that produces such a condition was the sinc function. This is the Fourier transform of a sinc function. So here a sinc function is shown, and here many sinc functions are actually shown. They are overlapping, but you can see that at the time instant 0, only the first one has the high peak, and at that time there is no overlap. There is overlap, but the amplitude or magnitude of all the other pulses will be 0 at the 0 time. If you consider the next pulse, it will have a high amplitude at time tb, but at time tb all the other signals will have a magnitude of 0. So they are not interfering with the amplitude of the specified pulse. So that is the property that we are using in this while we are using the sinc pulse for transmission. So this is the sinc pulse, and this is its frequency domain representation. Here it is again shown in color. ISI occurs. That means there is ISI. Here you can see that these dotted lines are the sampling instance, and in between the sampling instance there is a lot of ISI, but it is not getting affected. We are not getting affected by those ISI because we care about the sampling instance only. So at the sampling instance there is no ISI, only the threshold value of that specified pulse. That is the advantage of using such sinc functions as input signals or transmission signals. The limitation of the first criterion pulse or the limitation of the sinc pulse. We said that it is a infinite time duration pulse, so it cannot be practically created. Even if we try to create it using a filter, the filter's transfer function will be looking like this. So such a sharp filter cannot be practically implemented. So it is practically not possible to produce such a sinc function. And in the theory itself, we mentioned that at the sampling points, the ISI value will be 0. That means the sampling points should be sharp. There should not be any timing errors. If there is an error in sampling, that at all the other timings there is intersymbol interference. So if the timing is not accurate, there will be plenty of ISI. So timing is very much important in the case of sinc functions. So we are looking for a better alternative, for a possible alternative. So we are looking for a signal that produces a more gradual transition in the frequency domain instead of the sharp cut, and a signal that is more robust to timing errors, but still it should satisfy the Nyquist first method criterions. So raised cosine signal is such a signal that we found as an alternative for the sinc function. So this is a raised cosine signal. The tail is decreasing much faster than the SA function or the sample function or the sinc function. And here the synchronization errors will be lesser than that of the sinc function. And this is its frequency domain representation. Here R is the roll-off factor. For the perfect rectangular passband, the R value or roll-off value is 0, and when the R value or roll-off value increases, the bandwidth increases. So here the relation between them is also shown. When R value increases, bandwidth increases. When R value increases or the bandwidth increases, the ISI decreases. Let us consider a general model of digital communication system. In the block diagram, we have a input binary data which is represented by BK, a pulse amplitude modulator which has a carrier input of clock pulses, and the output is AK, the modulated output. Then there is a transmit filter. In the transmitter itself there is a filter. It is having a impulse response of G of t. The output is the S of t, which is the signal ready to be transmitted to the channel. The channel will have an impulse response of H of t, and in the channel the signal will get added to a white Gaussian noise which is represented by W of t. So this X of t will be a mixture of S of t and W of t, and in the receiver section you will have a receiver filter having a impulse response of C of t, and the output signal will be represented by Y of t. This Y of t signal is sampled at a time intervals Ti is equal to ITB, and then after sampling it is fed to a decision device. The decision device is already set with a predefined threshold value of lambda. So this sampled value and this threshold value is compared, that is the operation of this decision device. So after comparing, the decision device will decide whether it is a 1 or a 0. If the input sampled value is greater than the threshold value lambda, the decision device will decide that the output is a 1, and if the input value is less than the threshold value lambda, it is a 0. So this whole system has basically 3 sections. The transmitter will include a message signal, a modulator and a filter. In the channel there will be a channel filtering effect and a noise addition effect. In the receiver there will be a receiver filter, a sampler and a decision device. These are the impulse responses of the transmit filter, channel and the receiver filter. Now we shall see the formula for the received signal Y of t. The Y of t can be represented by this equation, mu into summation k ak p of t minus k tb plus n of t. In this n of t is the noise parameter, mu is the scaling factor that determines the amplitude of the signal, and P of t represents the overall impulse response of the system. Overall impulse response means the impulse responses of the transmission filter, channel and the receiver filter. This is convolution operation, so it is G of t convolution, H of t convolution, C of t. So this is the overall impulse response of the system. We assume that the impulse response is normalized by setting the P of 0 as 1, and the overall impulse response in the frequency domain can be represented as mu P of f is equal to G of f into H of f into C of f. This is the transmit filter, this is the channel filter, and this is the receiver filter. In time domain it was convolution operation, now it is multiplication. Now coming to the principle of operation of the receiver. The receiver filter output Y, the signal we previously considered, is sampled at a time Ti is equal to ITB. So the Y of t signal is sampled at time intervals ITB. the output signal after sampling will be like this. Here the first term will represent the original signal, original beta amplitude, that is mu AI. Mu is the scaling factor and AI is the signal level, and this is the noise N of Ti, and this middle parameter, this is the term that represents the intersymbol interference. This term will be consisting of all the amplitudes due to the remaining bits. That is why it is mentioned as k is equal to minus infinity to infinity except I value. So this term will represent the intersymbol interference. The term mu AI represents the contribution of the ith transmitted bit or the desired bit. So that is the signal level, and the term mu sigma k is equal to minus infinity to infinity ak p of I minus ktb represents the residual effect of all the other transmitted bits or the ISI while decoding the ith bit. This will happen for every bit. In the absence of both ISI and noise, the sampled output will be y of Ti is equal to mu of mu A. So that is the output signal. The situation where the ISI can be considered alone and the AWGN can be neglected. When can we neglect the noise? That is, if the signal to noise ratio is high, as in a telephone system, the operation of the system is mainly limited by the ISI alone. So in that cases we can just ignore the AWGN noise parameter, the N of T that we just saw in the previous equation. For distortionless transmission, the intersymbol interference ISI parameter should be 0, and also at instant I is equal to k, the sampler output y of Ti should be mu A, which is the message signal. So to make the intersymbol interference parameter 0, the condition or the criterion is P of ITB minus KTB is equal to 1 for I is equal to k and 0 for I not is equal to k. When I is equal to k, this parameter will become 0, which is equal to 1 because of the normalization that we assumed previously. So this is the Nyquist criterion for distortionless baseband binary transmission.